Dzień dobry. Hello, everybody. My name is Matthias Deeg.
I'm Gerhard Klostermeier.
In the next couple of minutes, we want to present new tales of wireless input devices. Yeah, as I said, my name is Matthias. I'm interested in IT security, and I think this should be enough.
Yeah, for me as well. I'm an IT security consultant / pen tester as well. Just interested in hacking hardware and radio.
Yeah, and the agenda of our talk, we have here 9 topics. At first, we want to introduce the use technology we have used and we have attacked. We want to talk a little bit about previous work of other researchers. We want to talk about our research and what is new, about the general attack surface and the different attack scenarios, the found vulnerabilities. We try to do some live demos and have sacrificed a lot to the live demo gods this morning, so I hope everything goes well. We additionally have some anecdotes concerning wireless input devices, and of course at the end some conclusions and recommendations for you. And hopefully some time for Q&A. Okay, so when we talk about wireless input devices, the next couple of minutes, we actually talk about the devices you can see here. So we are talking about wireless keyboards, wireless mice, and wireless presenters in this case. The technology behind it is radio technology, especially 2.4 gigahertz communication. And you have electromagnetic waves between those devices, and you have stuff like mouse action, mouse movements, mouse button presses, and of course you have keyboard events, keystrokes that can happen between the sender, for instance a keyboard or wireless presenter, and a receiver, usually a speed dongle you have to plug in into your computer system. Yeah, there has been a lot of previous work of other researchers within the last decade, actually. So it started back in 2010 with Kikoriki, where some wireless input devices were attacked by the people from Dreamlab Technologies. Then concerning wireless presenters, back in 2010, actually, there was a talk from Niels Teusing, who already showed how you can attack wireless presenters and own people, for instance, also live on stage. Then there was some research concerning the NRF-based device we are also using in a live demo a few minutes later by Travis Goodspeed. There were key sniffer hardware for sniffing attacks by Semikamkar. And then back in 2016, Mark Newlin published a lot of research concerning wireless input devices, publicly known as mouse jack, jack, and key sniffer. And our previous research back 3 years ago was also released publicly in 2016. It was Call of Mice and Keyboards. Yeah. And now we're here to talk about something new, and we are also answering some old questions. And independently to us, Mark Newlin also publicly released a few weeks ago some of his research he's also doing right now concerning presentation clickers.
Okay, so what's new? It's new tales of wireless input devices. So we want to ask, we want to answer the question we left out on our last research. The other important thing, the wireless presentation, or these presentation clickers, were not in the focus for our last research, and they became very popular, and we want to have a closer look at them as well. And in addition, a lot of people and customers came to us and asked, well, if all the wireless input keyboards are broken, can I just use a Bluetooth keyboard and everything will be fine? And we want, try to answer the question as well. So this is just for recap. So to highlight the second line, the Fujitsu keyboard was still open from our last research. We weren't sure if we can do keystroke injections. Just remember, this is a secured keyboard. It's advertised with AES encryption and being secure. And there we put together a list of several more devices, and most of them are wireless presenters, as you can see. And of course, like I said, we just went to Amazon in Germany and took the 3 most likely bought keyboards with Bluetooth technology from there.
Okay, so we had a look at non-Bluetooth 2.4 gigahertz devices and Bluetooth 2.4 gigahertz devices. That's an important point, because we will mix the vulnerabilities we found in both of those device classes, actually. So just as a reminder for you. So talking about the test methodology we've used, it's quite straightforward, and I think everybody who is doing this kind of research uses the same methodology in this way. At first, we try to do some hardware analysis, so we are opening up the devices. We have wireless presenters, keyboards, and even the dongles, the tiny ones. We start to look at the printed circuit boards. We try to identify the different chips that are used. We try to find documentation and hopefully also development kits that are publicly available. We try to find different test points that are on the devices that can be used for debug access or programming access, for instance. Sometimes we solder some wires to the PCBs for having debug access, actually, if it's not already there, and we also use logic analyzers in some special cases to analyze data communication between different chips, if we, for instance, have a two-chip design with a microcontroller and a separate transceiver. Then the second stage is the radio-based analysis. For this, we use all the popular radio or RF tools that are available, for instance, software-defined radios like Hacker F1, the Ubertooth one by Great Scott Gadgets for the Bluetooth analysis stuff. We have a crazy radio PA USB dongle and the NRF research firmware developed by Mark Newlin a couple of years ago, which is quite a handy, useful platform and also low cost. Then on the software side, we use typical RF analysis software like the Universal Radio Hacker, GNU Radio, and also in Spectrum to record, replay, and analyze all the radio communication we see that is going on with these different devices. And of course, we try to identify the used transceivers. If it was not possible by the hardware analysis, we try to do it by analyzing the radio signals that are recorded over the air. We try to fill our knowledge gaps concerning the packet framing, packet formats, checksums, and stuff like that. And concerning Bluetooth research, we use specific Bluetooth dongles that are well supported with the Linux Blues stack. Okay, and the last step is firmware analysis. To be honest, we only had a superficial look at firmware we could extract in this research concerning the Bluetooth devices. And this was due to limited time we had allotted for this Bluetooth research project. And concerning the non-Bluetooth devices, we have analyzed, it was not necessary to analyze any firmware because the goals we wanted to achieve, we could achieve by hardware analysis and the radio analysis at the first steps. Okay, on this slide, you can see a typical wireless presenter. I think most of you are familiar with this kind of devices. So in every conference or meeting room, mostly all over the world, you can find a device like this, for example, by Logitech. A Logitech R400 is a quite popular one. And these kind of devices are actually keyboards with a special form factor and only a limited amount of buttons. And the buttons you can see here on the slides, it's for the R400 by Logitech. It's actually only page up, page down, escape, F5, and what else do we have? The period, yes, on another button. So these are limited capabilities you are supposed to use when you're having a wireless presentation clicker or wireless remote like this. And there are different kinds of wireless presenters. For example, this is a wearable one. This is one I will try to attack in a couple of minutes. So this has the form factor of a ring, so you can just here put it on your finger during your presentation and have your hands free. So it's convenient in some places. And what you can see, also see here on the next slides is some internal photos of the PCBs and also the chips we've identified. So for example, here we can see a beacon transceiver. It's just a single chip technology. On another board here is a Logitech R400 wireless presenter. Here we have another kind of RF IC. It's a Nordic Semiconductor NRF24. This is another brand of wireless devices, Targus. Here we also have an NRF24 chip in there. Here you can see pictures of a Kensington wireless presenter. In this case, we were not able, by identifying the chips, doing just a hardware analysis and staring at the PCBs, because both chips, the microcontroller and the radio transceiver, are covered in epoxy resin. And what we did here is we just wiretapped the PCB traces under a microscope, soldered some wires, and analyzed the SPI communication, so the serial peripheral interface, and then checked some data sheets to find out what was actually the chip, or which chips match the SPI communication we could just sniff in this instance. And here I have some photos regarding the Bluetooth keyboards, the three we have analyzed. For instance, this is the PCB and the Bluetooth system on a chip used in the 1x1 keyboard by Broadcom in this case. This was a Logitech K420 Bluetooth keyboard. This also used the same chip but by another manufacturer. In this case it's a Cypress Bluetooth system on a chip. Yeah, and here you see the back of the device. In some cases, you already have some test points where it's just easy to sort the wires to and analyze stuff. Sometimes it's not that easy. Yeah, and here we can see a photo of the Microsoft Designer Bluetooth keyboard. And actually, we had to damage the metal case of the keyboard to gain access to the PCB because yeah, it's actually bolted in a small metal case within the keyboard itself. But it's still possible to gain access there.
So as you can see, we identified a lot of different transceivers here, and this is just an overview for you if you want to look them up. And we provided the USB IDs as well, so it's easy to identify them. Same for the Bluetooth ones. Another important thing for the analysis is, reading data sheets. I'm not going deeply into this, but a lot of the information is publicly available. If you read the markings from the chip and look up the data sheet, you can learn a lot about these chips. And sometimes they're the same, just from another manufacturer. Sometimes they are like clones, like the backend chips are nearly the same as the NF24. So this is really helpful, and there are some unknown chips where the data sheets are not available. But in one case, Mark Newland already reverse engineered a lot of these chips, and the information was also publicly available. Firmware analysis, you can do that too. As my colleague said, we didn't do that much. But in this example, the Microsoft keyboard did not enable the readout protection, so you can just hook a programmer to the keyboard and read out its firmware and all its secrets that are on there. So this is what the output looks like. So you get a dump file with the actual code. Then the radio-based analysis, we did that too. So software-defined radios, there are tools around now like Universal Radio Hacker, really handy. You can see much on this, but it's really easy to do the analysis phase of the signal, so understanding what the signal is. And if you understand what the signal is, it also has a generator built in, so you can generate the package in the way you want them to be, and send them with your software-defined radio.
Yeah, and the actual challenge you have when doing reverse engineering of radio protocols is turning a bit stream like this one here to something meaningful in order to achieve something like keystroke injection that is depicted in the image below. So this is what we did or tried to do in our research. And the general challenges in this reverse engineering process are finding out the proper signal modulation that is used for the radio-based communication, finding out the packet format or the packet framing that is used by the different identified transceivers we had. There are issues with field length. For instance, there are field lengths that are not multiple of 8 bits, so non-8-bit bytes. And when you start to calculate some checksums, for instance, and you only have an implementation for CRC that works byte-wise, you have to do some tricks concerning initial values to compensate odd field lengths, for instance. And there's always the issue with digital data concerning bit and byte orders, so you have to figure out in which bit and which byte order data is transceived from the sender to the receiver. And there's a lot of checksums going on in most of the protocols. Some checksums are vendor-specific and only regard the payload. And the other checksums are actually radio-specific and are depending on the wireless transceiver that is actually used. And of course, you have to find out the payload contents, so how the devices actually work, how they encode their data when communicating mouse actions or keyboard events from the keyboard or from the presentation clicker to the receiver, to the computer actually. And there is also something called data whitening. In some data sheets, it's also called data scrambling or pseudo noise code. I would not regard this as a security feature, but some vendors use it as a security feature, and it means that you can turn on an extra scrambling layer in your transceiver radio, and the thing that you send to the radio is not the thing that you can see over the air by doing a radio analysis. So you have a type of encryption actually going on, and this encryption is called data whitening in this case, and some people also call it data scrambling. And for this instances, you have to find out what are the initial values for the data scrambling, what might the data scrambling algorithm look like in order to be able to generate arbitrary packets that you want to send to the receiver, in order to find out if you can provoke or trigger some actions that are not actually intended by the manufacturers themselves. On this slide, you can see how a typical packet is looking when we're talking about 2.4 gigahertz communication, the non-Bluetooth devices we've analyzed. Usually we have a preamble, we have sync words, one or more. There may be an address field, a control word field, a payload, and there's the checksum at the end. And regarding control words, there are also different types of control words and control parameters supported by different vendors. Usually there is a field for the packet length or the payload length, the configuration concerning acknowledgements, and a packet ID. And yeah, it's important to note that not all fields are actually used by all 2.4 gigahertz transceivers. But that's a good blueprint for doing some educated guesses if you don't have access to the actual documentation of the chip you're analyzing. So for unmarked chip, for instance, just start with this and try to figure out what is used and what is not used. Why educated guesses and trial and error. Yeah, now on this slide you can see an actual example, turning a bit stream, so just a sequence of ones and zeros, to some actual meaningful data. And this is the packet format that is used by the Beacon 2461. Wireless presenter we've analyzed. It's called the Innertech Wireless Presenter 2002. And yeah, I've just described here all the different fields on the slide. So we have a preamble, a classic preamble with alternating ones and zeros. It's 1 byte in this case. We have a 5-byte address that is used to address a unique device. So if several people are using the same product in the same place, they will have different addresses, and the receivers and the senders are actually paired. So you can only talk from one sender to one specific receiver, and this is done by having a unique 5-byte address in this case. Then there is the control word. This is an odd length field in this case, because in total it's 9 bits long, so it's not a multiple of 8. So we have to do some tricks calculating the CRC checksums. And here we have a payload length of 3 bytes in this example. The packet ID is 3, and there are no auto acknowledgements required by the receiver. Then there is the actual payload. The good thing is the payload in all the instances we have found in wireless presenters is unencrypted. This means that if you know what you are looking for, you can see it unencrypted after you've demodulated the signal correctly. So here we have the clear text bytes 4B, 4E, 00 in hex. And actually the second byte of those, the 4E, is the human interface ID key scan code that we want to send to our computer system where the USB dongle is attached to. And in, I think, all cases of the presenters we have tested, there's also a 16-bit CRC checksum actually calculated by the transceiver itself. And there are also some more checksums regarding other wireless presenters and also keyboards which are integrated into the payload. So there can be more checksums, additive checksums, or by polynomial division in the payload itself, and you will also have to reverse engineer those checksums in order to generate arbitrary packets and to see if you can also send different events, different keystrokes to USB receiver, for example, in order to achieve a keystroke injection attack. Okay.
You can do it as well. So there are different attack scenarios in our case. They pretty much, you can think of them if you look at the devices. So you can do the physical ones if we have access to the device, like extracting firmware, manipulating it, or maybe getting the key material from there. It's, well, for presenters, there's not much key material there when they're not encrypting, but for keyboards there is maybe. And of course you can over-the-air attacks like replay attacks, just recording a signal, replaying it, checking if it's authenticated. Maybe you can input some keystrokes in an unintended way, and if it is encrypted, maybe there are ways to decrypt the communications. These are the 4 types of security vulnerabilities we found. So we found actually possibilities, well, there's not a good protection against reading out the sensitive data. The communication is, at least for the presenters, unencrypted and unauthenticated. And we have missing protection against replay attacks. So you can just record the signal and replay it and disturb the presenter with it. And we have cryptographic issues where we can inject keys at dongles that actually should not allow us to inject keys. So for the first one, this is rather obvious, like I said, going fast forward here. Especially for the keyboards, the Bluetooth keyboards, they had 2 of them had an external flash of them, so the actual microcontroller on there does not store the configuration data like the address to the dongle he's paired to the actual device it's paired to, and the encryption key, but it's on an external flash, so you can just attach to the flash and read it out. And in the case of the Microsoft keyboard, it was an internal flash, but the readout protection was not set, and you can just extract the firmware. We did not do this for the wireless presenters, because we don't have to. We got what we wanted without doing it.
Yeah, and there was also another kind of attack, mouse spoofing attacks. Also regarding wireless presenters, because some of the wireless presenters are not also a limited keyboard, but they also have mouse cursor functionalities. So they have a little joystick and you can move around the mouse cursor and also do some mouse buttons. So this was just a reminder that also mouse spoofing attacks we've demonstrated a couple of years ago are also a thing with wireless presenters. And it's also the same issue here. The communication is unencrypted and unauthenticated, so you can actually forge and generate your own packets, and by knowing the correct packet format, you can do mouse actions. And by doing mouse actions, you can also get remote code execution if you're doing it properly. And if the system you're attacking is unlocked and unattended for a couple of minutes, we have a YouTube video online since, I think, 3 years, and you can just
some screenshots.
Just show. Yeah, here, 2 screenshots of the video. So what you can do with controlling the mouse, you can open up
the on-screen keyboard.
A virtual keyboard. Yeah, that's the name I was looking for, the virtual keyboard. And then you can just type in your keystrokes on the virtual keyboard and do a classic download and execute attack vector using PowerShell, for instance, and have malware be downloaded from the internet and execute it. And this actually works, but it's not that reliable in most cases, but it works. We got it to work in some cases. Yeah, and you can execute malware ransomware, for instance.
So the other thing we talked about is replay attacks. I think they were covered here at the conference very well. So the most easy way is just to buy a software-defined radio, and you don't have to know anything about the protocol. You can just record what is sending, and if you send them the data again out with the presenter being off or the presentation clicker being off, we noticed that all of the presenters just are vulnerable to these replay attacks, because if you do like 2 slides forward and record this and then play it back later, it will go 2 slides forward. So there's no like counter or something protecting against replay attacks. Well, it's not that important for presenters, I guess, but if we have a wireless presenter here and you doing it from the audience, it's really annoying, for me at least. And we tested, of course, the Bluetooth keyboard, but for such a simple attack, the Bluetooth protocol has measures against this, so it didn't work on Bluetooth.
Okay, and the most interesting attack, at least I think, is the keystroke injection attack vulnerability. And yeah, here we have found quite a few. The problem concerning the wireless presenters we have tested is the same again. It's unencrypted and unauthenticated data communication over the air, disregarding data whitening. So if there is any data whitening that also uses some kind of encryption, we don't count it as actual encryption because we've bypassed it in 2 products, and yeah, it's not raising the bar for an attacker because he can find out how the data whitening is working and bypass it actually and use it for his own purposes. Yeah, and here the same story. If you know the packet format, have reverse engineered the framing, you can send keystroke packets to USB, receive a dongle, and then it will depend if the device is vulnerable or not. So if there is no input validation on the client side, I say, where the USB receiver dongle is attached to a computer system, then you will actually be able to inject arbitrary keystrokes or triggering USB HID keyboard events and have your keystroke injection. But we also had 2 devices from the, I think, 9 wireless presenters we have tested that were not vulnerable to keystroke injection attacks. So they actually did some kind of input validation on the USB receiver dongle side, some kind of data whitelisting, and they only accepted the 3 or 4 buttons that were actually present on the sender, on the wireless presenter. And that's the right thing to do, right? But all the other manufacturers and models, they didn't do this. So there's a security issue of keystroke injection attacks in most of the wireless presenters we have tested so far, and also other people have tested. As said in introduction, we also have some more information regarding AES encrypted keyboards, or one AES encrypted keyboard. We had a look at in 2016, but not too much. We found some time a couple of months ago and had a look at the Fujitsu Alex 901 wireless desktop set. And what we found out is that it was not affected by the same cryptographic issues we have found in other AES encrypted wireless keyboards. Actually, the 3 models you can see here, a Cherry, the Unlimited, the Logitech, and the Perix Periduo. Here's just a reminder how it worked back in 2016 and still works in some of those models who are not patched, actually. Here we were able to inject arbitrary keystrokes due to the insecure use of the AES counter mode. And having the possibility to replay packets that had the same counter value. So all those keyboards were affected by classical replay attacks, but we could also find out that the plaintext content of a key release packet is all zeros, like in this case, 11 null bytes. And then if we did the math and the crypto, we found out that all the things that are marked in red here are actually known to us as an attacker. So we know the ciphertext, we know the plaintext for some specific packets, namely key release packets. We know the so-called nonce that is used in the counter mode of AES, and we know the counter value because this value was also always sent unencrypted in the radio communication. And by knowing this, you can simply manipulate a recorded packet and manipulate it in such a way that you just change the key scan code that is encoded in one specific place of the keyboard. This place depends on the vendor we've actually tested, but it worked at least for the Cherry keyboard, the Logitech keyboard, and the Perix Periduo keyboard by simply doing a clever exclusive OR at the correct place with having some pre-gained knowledge. And that's the way you can achieve keystroke injection attacks against AES encrypted keyboards, and that's what we've showed in 2016. Now concerning the Fujitsu keyboard, we had another look at. It didn't work this way, but we just found out that we could send unencrypted keystroke packets to a USB receiver, and he just accepts them. So what we did is we had a look at the data communication, or the data sheets and development kit, and then just play it around with this specific chip. Use the same configuration we sniffed via a logic analyzer, in this case directly at the pins. Sorry. And then did our own implementation using a device like this. It's a do-it-yourself multi-protocol transceiver, actually used by the quadrocopter community. And we used this device to attack the Fujitsu wireless keyboard. And the hardest part actually was to find out that there's no hard part. You can simply send unencrypted keystrokes. You just have to read the documentation. Sorry. And that's it. So on this slide, you can see the pseudo noise codes. These are required for the data scrambling that is used in this keyboard, but two keyboards we have tested simply use different codes. So these are 10 recommended codes by Cyprus you should use. And yeah, the vendor is using the recommended codes, so they are no secret, they are publicly documented. Just have to do some trial and error. And concerning the payloads, they are quite simple. You just have key presses and key releases, and the second byte, or the second and third byte, are actually the HID scan codes and the modifier keys you want to send to your device. And that's it. That was really a simple one in this case.
Okay, so let's make a change and talk about Bluetooth and the Bluetooth, well, trust relationships. It's rather obvious for somebody who is really into Bluetooth. I will go quickly over this. I think we have like 50 minutes left and we want to show you live demos as well. So just for the obvious, well, if you pair a device with Bluetooth, there's cryptographic key material on that, well, on that smartphone, for example, and for example on that headphones like this one. And another interesting observation we made is, well, it's very well known actually, but the cryptographic key material is not bound to any specific properties. So let's go through this. If you, well, first interesting thing, if you pair your headphones with an Android device like this, it automatically gives you a lot of access to like phone calls, media, audio, and I think this, we can abuse this later, and there's another interesting feature like the Android Smart Unlock. I think it got introduced in like Android 7 or 8, I'm not sure anymore. But it's basically, if you pair a Bluetooth device, you're getting asked, do you want to unlock your screen if this Bluetooth device is near your phone? So could be very handy. And a security risk as well, of course. And the attack we want to demonstrate in about a minute is, so just you can follow me from the idea behind that is, if you, well, leave your headphones somewhere on the train or lose them, or maybe just give me 2 minutes to access them, well, unscrew 4 screws. There again is our external SPI flash, so we can easily, well, one method were like desoldering the chip and soldering out on a breakout board and plug it into a universal programmer, then you can read out the chip. But it's actually much easier with an adapter like this. So there's a pogo pin adapter. It has like springs behind the pins, and you can just don't have to do any soldering, just press it on the chip and you'll do the programming thing, say read out, and you come up with something like this. And well, it's marked in green and red. Sorry for the colorblind. And it's basically, well, you just look at the dump you got and you see the address of the smartphone where the headphone is paired to, and the actual key that is used for the encryption with that smartphone. The address is somehow, well, funny formatted. It has some zeros in there, and the byte order is a bit different, but well, by looking at it, you will find your way around this. So interesting thing first is that during the pairing process, there are a lot of, well, access granted automatically. And if we can read out the key and emulate a device like this, for example, a headphone, we can, well, exploit these, not really exploit, but we can use these functionality that is granted. Like, for example, in most cases, there's phone book access. So if we read the key, we can just run a tool. I think it's, well, on the next slide. Sorry for jumping forward. It's from the BMW group, just a simple Python script that you can use with Bluetooth to read out the phone book of a device. So you can just get the keys, put it on your Linux laptops, use this Python script, and there you go with the phone book. And more interesting, at least for me it was, if we have the key and the address, we actually can change the capabilities of the Bluetooth device. So what was once before a headphone can become a keyboard with these, and the device does not care at all, at least an Android device or an iOS device did not. We checked this on several versions of the devices. On Microsoft and Linux, it did not work. I'm not sure of technical issues or if it's actually for security reasons. but on all other devices we just can change this. So let's come to the interesting part. Let's hope this stuff will work. We want to show you the Bluetooth, like this one I just talked to you about, the Bluetooth trust relationship issue. We want to attack a wireless presenter, of course, and the AES encrypted keyboard. So let's start with the Bluetooth one. Okay, sorry. So we have here just an Android phone. I can show you. Well, it's locked with a super secure pin of 1, 2, 3, 4, and it's already paired. I guess I can show you paired devices. Okay. Well, it's hard to see. I don't see it anymore. Oh, sorry, I was on pair new device, previously connected device. So there you see your headphone. We don't do the reading out here live on stage, but trust me, it's just a normal headphone where we extract the key, and there's a Bluetooth keyboard emulator for your desktop, so it's just a Python script. My colleague ported this script to Python 3 and Blues 5. And maybe we will see it in a minute if everything works out. It gets connected, and you see the small symbol with the lock got unlocked down there. And now we can, so I'm not tipping on the visual side, so this is just me emulating a keyboard, and I can do.
I think I will have to do it because
other
different keyboard layout.
Keyboard layout.
So, yeah, what it just is, what you can see on the left is our keyboard emulator. So you're emulating a USB Bluetooth keyboard. We gave this emulator the link key we've extracted physically from our headphones, the target device with one-time physical access. And on the right, you can see the Android phone we are now targeting. And the Android phone was previously paired to a Bluetooth headphone. But now what we have is we have actual keystroke injection here, because now we have a full functional keyboard. And now we can trigger arbitrary actions like calling some people and doing other stuff in this way. Yeah, and that was interesting for us because we didn't know that you can change your capabilities of already paired Bluetooth devices in this way.
I think it's not true for all Bluetooth, like Bluetooth Low Energy handles this different. Most of the headphones, because the audio profile is Bluetooth Classic, you're still able to do this. Okay.
Yeah, so that was a short demo of the exploiting Bluetooth trust relationships. Okay. Now the next demo, I think, will be the wireless presenter.
Yeah.
Okay. Let's switch this.
So this is exploiting this one. I leave it on here, so I'm not pressing any keys. And
yeah, so we are taking the Inattack
you have to
W
start the camera.
Oh, I have to start the camera.
You can see the
right.
victim machine. Sorry.
Let's see if it works. Yeah, so we have picture in picture. Oh, no, wrong. Right. Okay, so I will just move it a little bit down. Yeah. So what I'm using here is just a new tool. We've already uploaded to GitHub this morning, so you can all do this kind of keystroke injection attacks against different wireless vulnerable input devices, for instance, presenters. It's based on a tool released by Mark Newlin a couple of weeks ago, I think on the 20th of April, and we want to extend it with the knowledge we have gained from our research, and Mark Newlin is also doing some research. So check out this GitHub repository if you're interested in injecting keystrokes to some devices. And what I will use here now is the infamous Crazy Radio dongle that is actually used for controlling or radio controlling quadrocopters, but it can also be used for attacking computer systems via radio. And now?
The dongle is in the victim system, of course, downstairs.
Yeah, so here in the screen you can see our victim system running a Windows 10 operating system in this case, and the USB receiver dongle of the vulnerable Inattack presenter is just attached to this device. And now I will
Let's
try. Yeah, and in this case it worked. I don't know, can we zoom in a little bit with the camera? I don't know
like
if
manual
autofocus
like
is working.
Camera.
Yeah.
No, I don't think you.
Some shaky cam.
So you can basically input like download and execute shell codes or something
Yeah,
like this.
so that was just the first demo. So what we can do here now from our laptop, we can send arbitrary keystroke commands to a remote system.
Let's move on to the next. So let's move on to the next demo. Now I'm plugging in another dongle. This is the dongle from the Fujitsu keyboard, the AES encrypted version.
Yeah, and in this case, I haven't ported the attack yet to this keyjector tool, but I'm trying to do in the future. What I have here is my proof of concept setup I've done. So here I have this do-it-yourself multi-protocol transmitter device. It's actually an Arduino-based device here, having 4 different 2.4 gigahertz transceivers on them. One of them is the Cypress 6936, I think, which I'm actually using, and the rest is just a power supply. I didn't have a better power supply here. It's just a battery. And what I will try now, I will just power on the device, and let's see if we can pop a command shell again. So 2 seconds delay, I think, and then there should be some actions. Yeah, and we have again pop the command shell, and we can enter arbitrary passwords, or we can just execute PowerShell download and execute script. For instance, if the device is internet connected, download malware as we wanted and start it. And this kind of attack can happen in a couple of seconds, actually. So if you have an unattended device near you, and near means physical proximity, so depending on your radio equipment, I think, 1 meter to 30 meters should work, actually. If you have a better sender, even more.
The crazy radio says in its data sheet it's up to 1 kilometer, but I think it's because of there's an actual amplifier on there, and I'm not sure if it's really working.
And it's side of view, so exactly. Indoors it doesn't work 1 kilometer, but
it's a question of the equipment. So.
Yeah, it's a question of the equipment, but that's how you can do keystroke injection attacks against
encrypted keyboard.
Encrypted keyboard in this case. So this was actually encrypted. Okay, we also have some proof of concept videos online if you want to see it again.
I think, do we have time to do them? Like 2 minutes.
Okay, we also have some anecdotes on the slide. I will just go over them very quickly. Product rebranding was an interesting issue. So 3 years ago, we've tested the Cherry B Unlimited AES. Now it's sold as B Unlimited 3.0. It uses the same 128-bit AES encryption with the same security issues. And people are still buying this new keyboard, the 3.0 version, but they're not aware of that it's vulnerable to keystroke injection attacks and replay attacks, where you can remotely take over a computer system.
So it's secure now because it's no longer advertised as being secure.
Yeah, so that was the solution by the vendor. Rebranding the product. And there are also some other anecdotes, but I don't have time for this. It's concerning CVS base scores, but you have it in the slides. Yeah, CVS base scores, you can come up with different scores for the same issue, and you have good arguments for it, and just pick the score you like best in the end. So that's the story for this one.
Also interesting on this one because the R400 is very well known, the presenter of Logitech, but we actually managed to just went to Amazon and buy 3 times the R400 from like different vendors, and what we got there were 3 different versions of it. So completely different hardware, and we talked to Logitech, well, which one is the real? Are the others fake? Are the others another manufacturer? And well, they don't want, or they could not. The ticket was basically just closed and saying, well, we can't say anything about that.
Yeah,
so I'm not sure if this is
up to now they couldn't help us. So we assume that only the left one shown here is real because it was the only one with a USB vendor ID owned by Logitech. The other ones didn't. So maybe the other ones are counterfeit products, but we just don't know. And Logitech just didn't tell us.
So conclusion, doing this quickly as well. For every vulnerability, No, for any issue, we found an actual vulnerability that can actually be used. So insufficient protection, well, we can read out the data. If it's unauthenticated, we can do mouse spoofing or keystroke injections. Well, if it's not protected against replay attacks, we can do replays. So there's a lot going on here. And if the cryptographic issues are not taken care of, we can do keystroke injection as well. For Bluetooth, some takeaway, we're coming to the recommendations in a second, is that every device needs protection because it holds your key. And something we did not speak about a lot, the stacks from the operating system behave really different. It's an interesting thing to look into for more Bluetooth experimenting analysis. So Bluetooth keyboards, we tested them. All of them we could read out, and 2 of them had insecure pairing where you can, well, sniff the key, or if you were present at the pairing process, you can reconstruct the pin that was needed. For the presenters, it's pretty much the same. So,
yeah. So it's just a summary as a table. You can see we've tested these 9 devices, and 6 of them are definitely vulnerable to keystroke injection attacks. 1 we have to do some work on, it's the Kensington one, and 2 were not vulnerable, at least what I found out, to keystroke injection attacks. And 3 are actually vulnerable to mouse spoofing attacks because they have the mouse features available to them as well.
Yep. This is a list of Mark Newlin. He tested a lot of presenters as well, so just look up his research as well, and you have a good list of presenters that are vulnerable. But if you can see here, the keystroke injection column, it's all green, and for us, it's almost all green too. So maybe not a good idea to use these devices. And for the keyboards, we can now say for sure the AES encrypted Fujitsu keyboard is vulnerable to keystroke injections as well.
I've just included this slide because it's a good example that security vulnerabilities may be re-implemented in another product version or product division, because the Logitech R400 was known to be vulnerable since 2010 publicly. It was based on another technology back then. It was a Cypress RF69103 transceiver that was used. Then, I think around 2013, there was a new product version of the Logitech R400 that uses this non-semiconductor nRF24 transceiver. And in 2016, we found, hey, this new version of your product has the same vulnerability as the one found back in 2010. And if you buy them on Amazon today or any other marketplace, you will still get vulnerable Logitech R400 devices.
So short recommendation, choose your wireless presenter wisely because, well, we only found 4 of them not being vulnerable to keystroke injection. For replay, they are all vulnerable. I'm not sure if I want to go over all of them. For Bluetooth devices, as I said, it's really important to keep your life cycle, to keep it clean. If you lose your headphones in the train, just delete the connection you have left on your phone because it's an access basically in your phone. So keep mind of that.
I think the most important takeaway is the last one. If in doubt, use wired input devices. And
if your company want to buy wireless devices, please at least use Bluetooth. Until proven otherwise, they look more secure than the proprietary versions. So there are a lot of other research going on in this area. Mark Newlin, as we told, still researching on it. And Markus Mengs, another German security researcher, is publishing more vulnerabilities on Logitech, specifically to Logitech receivers. Really interesting work. Just follow him if you want to have more information, and well, our code will be on GitHub.
Yeah, it is already on GitHub, so if you're interested in playing around and annoying some other speakers now this afternoon, no, you shouldn't. You can just do it. So the code is public, open source, publicly available. Yeah, and you should also think of that also barcode scanners, like the one shown here, are just keyboards with a specific form factor. And be prepared, we will publicly disclose some security vulnerabilities in a couple of weeks or months.
Yep. So or here's references if you want to read them. And
thank you very much.
Yeah, thank you very much, and sorry for the 4-minute delay.
Thank you so much, guys. Are there any questions? Oh, there are.
Maybe we do the questions later because we're already late. So just meet us outside.
We will be here the rest
We
of
have time for one quick
okay.
question. So
Okay.
Shoot. Sorry.
So, can you recommend any wired presenter remote?
We can actually recommend only, let me see.
There was.
Yeah, maybe this one, the August wireless presenter. But I've already bought this back in 2016, and I think it's not available anymore on Amazon. I couldn't find it again. But this was one that was not vulnerable to keystroke injection and neither to mouse spoofing attacks.
But replay, so you can still annoy the.
Yeah, you can
keys.
still annoy some people by doing replay attacks, but it's not as interesting as doing actual keystroke injections with arbitrary keys. A keyboard, a wired one actually.
A wide one, maybe a Bluetooth one, but
Yeah,
mainly wired.
and if not wired, then Bluetooth Low Energy. So we think Bluetooth Low Energy is.
And if you
It's
could
the way,
just
but it's
Bluetooth
still-
Low Energy like 4.2, they implemented in 4.2 a more secure pairing mechanism. Hopefully this keyboard uses the more secure pairing mechanism. So it uses Diffie-Hellman by then, hopefully, and the pairing process will be secure as well then.
Yeah. And we only had a look at the 3 Bluetooth keyboards we showed here, so it was 2 times Bluetooth Classic and 1 Bluetooth Low Energy. So there's more research to be done, and I hope other people will also join this research effort. Yeah. So thank you.
Thank you for the talk. I have a question about the Bluetooth attack with the headphones and substituting headphones with a keyboard. Have you looked into the Bluetooth standard? I was wondering if the standard considers that as an attack surface or not, because sometimes they go for some trade-offs, you know, like some.
Yeah.
So I was wondering what's your view on that? Thank you.
Actually, I've tried to find it, but the Bluetooth standard or standards, it's, I don't know, 5,000 pages.
Yeah.
And using my grabbing skills, I couldn't find a location where this issue was already thought of in the standard. But it could be.
Well,
Actually, it could be. But we don't know. But what was interesting is that different stacks we've tested concerning different operating systems just behave differently. So if there is any recommendation by the standard, it's open for interpretation at least.
Yeah, and maybe you can talk back there to Slavomir. He's there. He's a Bluetooth expert. Maybe he knows whether it's in the standard or not. I'm not sure, but it is known.
okay, thanks guys.